This video is on nucleophilic substitution reactions, specifically the two different mechanisms by which nucleophilic substitution can occur, and understanding how to know which mechanism will occur and be able to draw each type of mechanism. So there are two different ways in which this reaction can occur, known as mechanisms. They are known as SN1, nucleophilic substitution type 1, and SN2, nucleophilic substitution type 2. Now in SN1, how you can tell that a reaction is SN1 is if you have rate data, rate information, the rate equation will be first order, and there will only be one molecule involved in the rate determining step. Overall, this mechanism requires you to draw two different steps, and unlike SN2, this reaction can, but not always, can result in the inversion of a chiral center. And if you have an SN1 reaction happening on a chiral carbon atom, you will always end up with a racemic mixture or a racemate. So I'm going to go and explain the mechanism. So there are two steps. The first step is the molecule, the monohaloalkane. What happens is that the carbon-halogen bond breaks. Now it is important that we recognize that the first step, you start your arrow from the bond and you end up on the halogen. Okay, make sure you draw your arrow going from the carbon-halogen bond and ending up on the halogen itself, in this case chlorine, and you end up with a positive ion, and that positive charge is on the carbon, and we call that a carbocation, and we then have our chloride ion. So the positive ion is a carbocation. You need to know that. That term carbocation is really important to lots of different mechanisms, and the stability of a carbocation is what determines whether or not a reaction can proceed through a few different mechanisms. The positive charge must be on that central carbon. And the carbocation is an intermediate, and it is trigonal planar. It's really important that you remember, because it is trigonal planar, it is a flat molecule, which means that both sides of the molecule are open space. So when the nucleophile comes in to attack the molecule, it can do so from either of those free sides. So the second step is our nucleophilic attack. And in our nucleophilic attack, we show our arrow going from our negatively charged nucleophile, or specifically draw on two electrons to show that it's a lone pair of electrons on your nucleophile, attacking the positive carbon in the center, and you form a bond between that positive carbon and the negative nucleophile, and so you will end up with that final product. Remember that because it is a flat molecule, that hydroxide ion in this example could have attacked from the left hand side or the right hand side of the molecule. And this is very quick, so this is not a rate determining step. The previous step was a rate determining step, and it only involved the haloalkane itself. And as I said, because the carbocation is planar, the nucleophile can attack from either side, which can sometimes lead to a mixture of two different optical isomers in a racemic mixture. Now the second mechanism, the nucleophilic substitution type 2, shortened to SN2, this involves two molecules within the rate determining step. And overall, there's only one concerted step by which this reaction occurs by. However, you do need to be able to draw an intermediate to this reaction. If you have a chiral carbon involved, you will always get that chiral carbon switching from one form to the other because of the way in which the mechanism proceeds. So we will see this mechanism. In an SN2 mechanism, we need both the nucleophile and the haloalkane involved throughout. So the nucleophile will directly attack the haloalkane from the opposite side of the molecule to the halogen. So if we have our halogen on the right-hand side, as we do with that bromoalkane, the hydroxide ion, or nucleophile in this case, will be attacking. Now on this page, for clarity, that arrow is going to here, but this arrow should technically finish on the carbon atom, because that's what it's attacking. Now we can see here that our intermediate, because we had a negative ion attack a neutral molecule, the intermediate is negatively charged, and we show it in square brackets. And that negative charge is spread over the entire molecule. That's why we use the square brackets. Whereas in SN1, we showed the positive charge on the carbon because it was localized. The other important thing to note is the nucleophile comes in with a partial bond, and the halogen goes to being a partial bond. That's what those dashes mean. Those are your two weakest bonds. That's how we can say carbon's forming 5 bonds, because 2 of them are partial and 3 of them are full. Then what we see happening is this bond here. We see the electrons go from the bond onto the halogen, which then allows us to form our bromine ion and our new alcohol. So this arrow definitely needs to be on. So remember, it's going from the bond to the halogen. Make sure from the source of the electrons to where the electrons end up. So the intermediate in this case is trigonal bipyramidal, and it can actually go backwards because the OH group can add on and then can just fall off again. Or if you're pushing the reaction to completion, the halogen will come off. Remember those 2 partial bonds, square brackets around it with a negative charge, and you need an arrow showing that the carbon-bromine bond is broken with the electrons ending up on the bromine. And all the groups around the central carbon, you can see on the left-hand side, the groups were pointing to the left. When the reaction is completed, the groups are now pointing to the right. This causes an inversion of that chiral center. So how can you tell which mechanism will happen? So there are 2 ways. The first one can be if you're told about the rate of reaction, that's been determined experimentally, you can say if it's a first order reaction, it must be SN1. If it is a second order reaction, it must be SN2. That's straightforward. You're not always going to have access to rate data, in which case you have to judge it based on the type of haloalkane, whether it is primary, secondary, or tertiary. So remember, when it comes to nucleophilic substitution, it is the rate determining step that affects the order of reaction. The SN1 reaction only has 1 molecule in the rate determining step and is first order. So the rate is determined only by the concentration of the haloalkane. In SN2, you have both the nucleophile and the haloalkane involved in the rate determining step. So overall it is second order. However, it is only first order with respect to both the haloalkane and the nucleophile. And the rate expression will be rate of haloalkane, rate of nucleophile. So you can see between those 2 there is obviously a significant difference, and an SN1 reaction will not be affected by changing the concentration of nucleophile, whereas an SN2 reaction will be altered by changing the concentration of nucleophile. Right, how else to determine SN1 or SN2? So if the The order of reaction can only be determined experimentally, and in many cases you will not have access to this information. So there are other ways to judge it. These are judging the stability of the carbocation intermediate that would form during an SN1 reaction. That needs to be stable if the reaction is to do SN1, and also something known as steric hindrance or steric effect, which could prevent the reaction from doing an SN2 reaction. So we'll talk about carbocations. In SN1, the intermediate is a carbocation. That carbocation involves a positive charge being on a carbon, and that is exceptionally unstable for carbon atoms to be in that way. And it must be stabilized by the other atoms or groups bonded to the carbon. Where you have other carbons, and particularly carbon chains, bonded onto a carbon atom, they are able to push electrons towards the carbocation in something known as the inductive effect. And by pushing carbons towards that positive charge, you're stabilizing it. And if you've got a stable carbocation, that carbocation can exist and you can do SN1. So the more carbon chains coming off the carbocation, the more likely SN1 will occur. So tertiary haloalkanes are typically involved in SN1 reactions and primary ones are not. So if I illustrate that, or if I draw a carbocation in black, if I have hydrogens around it, forgive my writing, these hydrogens have no effect. So there's no stability. No stability, so no SN1. And that is for a primary one. However, if I were to do a tertiary one, we would have our carbon positive, and then we would have, say we had a CH3, and then maybe a CH3, CH2, and then another CH3. Well, each of these bonds has an inductive effect which pushes the electron density towards it. So that's electrons pushed. And that's called induction. Now, where you've got that, it stabilizes it. So we end up with SN1. So the more carbons you've got, you get more of this induction or inductive effect, which stabilizes the carbocation. Stable carbocations are responsible for the majority of the mechanisms you have to learn. The second thing is the steric effect. Now, the steric effect is what either allows or inhibits the SN2 reaction. Now remember, in SN2, the nucleophile is always attacking from the opposite side of the molecule to the halogen. So the bigger the size of the groups that are pointing away from the halogen, the harder it's going to be for a nucleophile to get past them towards the carbon. And if it's unable to get to that carbon atom, it will not be able to form the intermediate or do SN2 reaction. And we call this blocking due to the size of the groups the steric effect or steric hindrance. So I will illustrate what we mean by that. So say we've got our halogen here, that's chlorine, and we've got H, H, H. And these are all bonded. Now, H groups are small, So our our nucleophile can easily get past to attack. Whereas if we had, for example, we had CH3 groups, we've got H, 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 and then H, H, H. Our nucleophile here is going to find it really difficult to get towards that. So the nucleophile ends up being blocked. Oh, my writing is atrocious here. Nucleophile blocked. And that is steric hindrance. So for a primary one, you can get nucleophile attacking, you can do SN2. So you can get SN2, it's possible, but for a tertiary one, SN2 cannot happen. You can also get a steric effect if the halogen is attached onto a ring, and that ring is unflexible, so will not be able to move, so it's going to make it difficult for a halogen to be involved. But the obvious things for primary alcohols, for primary haloalkanes, you cannot stabilize the carbocation, so it cannot do SN1. There is no steric hindrance, so it definitely will do SN2. For a tertiary haloalkane, you have got the ability to stabilize the carbocation, so it will do SN1, and you've got massive steric hindrance, so it is blocked from doing SN2. Secondary haloalkanes, it's going to be hard to predict just by looking at the molecule which mechanism it's likely to do. And for a secondary alcohol, it's likely that you would be given rate information to come to a conclusion. So how do we determine? So primary haloalkanes, SN2 will occur because you have an unstable carbocation and low steric hindrance. Tertiary haloalkanes, you've got stable carbocations and high steric hindrance, so you'll have SN1. And for secondary ones, it's going to be dependent on the specific groups attached to the carbon bonded to the halogen, so it is unlikely to predict, and you would likely have rate data information. This slide here is really important because if you're asked to give a justification for a mechanism, this is what you need to talk about, specifically the stability of the carbocation and the degree of steric hindrance. Okay, so if you're asked to justify it, you always want to talk about the carbocation's stability and the degree of steric hindrance. So this has been a long video. We've detailed the two different mechanisms. We've explored how to know which one happens based on rate information and then based on the stability of carbocations that can form and the degree of steric hindrance.